Hi and welcome to the second video of my playlist about the best methods to reduce carboxylic esters to primary alcohols. This presentation is about reductions with metals, such as the Beauvoir-Blanc reduction. Although not as inexpensive and clean as catalytic hydrogenations, metals such as sodium or lithium are still relatively cheap. Alkali metals were the most common reducing agents before the discovery of boron and aluminum hydrides. Reductions with alkali metals always proceed by stepwise single electron transfer. Thus, the first intermediate is the radical anion sketched here. This radical can be long-lived because a second electron transfer would lead to a highly energetic dianion, which is therefore not readily formed. In the presence of alcohols or liquid ammonia, however, a fraction of this radical alkoxide will be converted into a neutral radical by protonation, as shown here. The neutral radical will accept a second electron more readily than the anionic radical. Thereby, an extremely basic metallated hemiacetal is formed that will be immediately protonated by any proton source available. The resulting aldehyde, being more electrophilic and sterically more accessible than the starting ester, will undergo reduction by twofold single electron transfer faster than the starting ester, and aldehydes are therefore almost never obtained as byproducts in these reactions. Thus, 4 equivalents of sodium are required to convert a carboxylic ester into a primary alcohol. Reductions of esters, ketones or aldehydes with alkali metals only work in the presence of proton sources, such as alcohols, amines or ammonia. In the absence of protons, the initially formed radical anion will dimerize to a 1,2-diketone, which is reduced once more to an acyloine dianion. Acyloines will be obtained as byproducts if too little Protex solvent is used. A further potential side reaction is a fragmentation of the initially formed radical anion into a carboxylate salt and an alkyl radical. In the case of benzyl esters, this can become an important side reaction, but with methyl esters and at low temperature, this reaction pathway is not critical. Let's now check some specific examples. This is an optimized Beauvoir-Blanc reduction of a hydroxylated oleic acid ester. With tertiary amyl alcohol as proton source and only a slight excess of sodium, a high yield of diol was obtained. Here, the reaction was performed with molten sodium. If a lower reaction temperature is chosen, the particle size of sodium will be important, and a larger excess of sodium may be needed because no complete conversion of the metal can be attained. Also, if a more reactive alcohol is chosen, for instance ethanol or methanol, then a larger fraction of sodium will be lost by direct reaction of the alcohol with sodium. Secondary and tertiary alcohols are therefore better suited as proton sources for these reductions. Alkali metals are powerful but not very selective electron donors. Therefore, a number of other functional groups may be reduced too during Beauvoir-Blanc reductions. In this example, both an ester and an oxime were reduced simultaneously by treatment with sodium and propanol. Aryl and alkyl halides as well as electron-deficient alkenes can also be reduced by sodium, as shown here. 2 and 4 bromophenols are, however, particularly reactive, and catalytic hydrogenation or other reducing agents would also cause a debromination of this starting material. Sometimes better results can be obtained with liquid ammonia as solvent, as in this example. Carboxylic acids will be converted into sodium carboxylates during such reductions, but will usually not be reduced further. In this example, a polyfunctional ester was reduced with lithium in liquid ammonia. A benzyl ether was also cleaved, but an alkene and an acetal remained unchanged. One further potential side reaction is the Birch reduction of arenes, as in this example. With a large excess of lithium in ammonia, an ester, an electron-deficient CC double bond and a phenyl group were reduced in high yield. The final isomerization of the alkene into the conjugate position could have been prevented with a milder method of enol ether hydrolysis. Birch reductions can be prevented by lowering the excess of alkali metal. Here, an ester containing a similar methoxyarene as in the previous example and an alpha-beta unsaturated ketone was treated with lithium in ammonia, without any additional alcohol. Only the ester and the electron-deficient alkene were reduced. The ketone escaped reduction by enolate formation. Only few examples have been reported of the reduction of esters by magnesium. These reactions are limited to particularly reactive esters, or certain esters with heteroatoms in alpha position. In this example, an ethoxycarbonyl indole was reduced to the alcohol by treatment with magnesium and methanol. Calcium is a stronger reducing agent than magnesium and seems to be well suited for reducing esters. In this example, a non-enolizable ester was reduced with a large excess of calcium in liquid ammonia. A ditioacetal was also cleaved, but an alkene remained unchanged. Treatment of the same starting ester with lithium aluminum hydride led to a selective ester reduction without cleavage of the ditioacetal. So, what other potential side reactions do we have to expect in metal-mediated ester reductions? Although the stationary concentration of aldehydes in these reactions is low, aldol or pinacol coupling products may in principle be formed, and may be a reason for the low yields sometimes obtained. If too little proton donor is available, acylene condensation or radical fragmentation products may also be formed. Metal carboxylates can usually not be reduced with alkali metals, and water should therefore be avoided. If the oxygen-bound alkyl group of the alcohol component of a given ester can form a stabilized carbanion, fragmentation of the metallated hemiacetal may occur, as shown here. This, like the radical anion fragmentation, would yield sodium carboxylates and the deoxygenated alcohol. Enolizable esters may also undergo Claisen condensation if the concentration of reactants is too high. In general, all dimerization reactions will be slowed down by diluting the mixture with an inert solvent. If ester dimerization yields 5 or 6-membered rings, then such side reactions can be difficult to prevent. This here is an example of a normal intramolecular acylene condensation conducted in the absence of any proton source. The intermediate acylene dianion was then reduced by the excess sodium to a diol just by dilution with isopropanol. Other functional groups can also be reduced by alkali metals. These include alkynes, electron-deficient alkenes, pyridines, oximes, nitro groups, arenes, alkyl and aryl halides, and benzylic ethers or thioethers. You'll have to determine case by case if ester reduction is faster or slower than any of these other reductions. This here is an example of the reductive deoxygenation of alcohols discussed above. This side reaction is only of concern when trying to reduce lactones with metals. Strained bonds, such as those in cyclopropanes, epoxides, or some cyclobutanes, may also be cleaved upon treatment with metals of the first or second group. Here, for instance, the cyclopropane was cleaved by sodium at 0 degrees Celsius in only 5 minutes. Also, alkynes can be reduced by sodium to alkenes, as shown here. Again, the reaction was fast at 0 degrees Celsius, also because sodium was used as a dispersion in oil. Esters near alkenes sometimes cyclize during reductions, as in this example. Here, the high yield was also caused by the favorable conformation of the starting ester. Unbranched, unsaturated esters do not usually cyclize in such high yields. Occasionally, aldehydes are obtained as byproducts, but this is only rarely seen. In this example, 4 equivalents of calcium were required for a complete reduction, and the slight excess employed was not enough to attain clean product formation. On a previous slide, a similar reaction was performed with 26 equivalents of calcium, and almost 80% of primary alcohol was obtained. Here are some further examples, including reductions with samarium iodide, which also proceed by single electron transfer. These references are also in the description of this video. The next video on this playlist is about the reduction of esters with boron hydrides. These reagents, discovered in the 1950s, are easy-to-handle, versatile reducing agents which have largely supplanted metals in laboratory-scale ester reductions.